Alright, so guys, please grab a seat. You guys should have your worksheets out in front of you. I'm going to give you guys 4 minutes to knock out these questions on your challenge for today. Again, feel free to look back at your notes and use yesterday's notes to do these, but they should be fairly straightforward. Try them out. Alright, let's go. Alright folks, please put your pen down, give me your attention up front as we go over all these problems. Alright, so we have the following 4 questions. The first one's a straight up units question, which can be very helpful if you're reading a word problem. It doesn't always say force equals or mass equals or acceleration equals. Sometimes it'll just say something like 8 newtons or 3 meters per second squared. And you have to know based on those units what you're actually pulling out, which variable it is. Alright, so for force, which is a capital F in an equation, it's measured in newtons, which is a capital N. Alright, mass is a lowercase m, it is measured in kilograms. And acceleration is a lowercase a, and it is measured in meters per second squared. I don't need you to write down those full sentences, so if you are, I'm not going to hold on this slide long enough for you to write them down. You should just be writing F is in N, M is in kg, A is in meters per second squared. And if by this point you don't have them written down, grab them from your worksheet, because you should be able to find them in various word problems. Question number 2. One can observe Wile E. Coyote running off a cliff. Using Newton's third law, please explain why as he is running in midair, he eventually falls. Why doesn't he fall when he's on the cliff? So he's running, he falls once he gets off of the cliff, just like you would if you ran off a building, you would fall. So the question I'm asking is, how come you don't fall when you're on the building? So right now you're all sitting on the first floor, we're not falling. We could be falling. If the floor kicked out from underneath you, you'd fall towards the center of the earth, right? So why aren't you falling based on Newton's third law? Alright, and the answer to that's really simple. Newton's third law is action-reaction. Therefore, if you push down with however much you weigh, if you weigh 150 pounds, if you push down with 150 pounds, the ground has to push up with 150 pounds. That's how it works. If you push down with 150 pounds and the ground can only push up with 140 pounds, guess what? You're breaking through the ground. That's what happens if you jump on a table. If you ever saw on YouTube that famous video, the big girl, she stands on a little coffee table and she falls through it. That's that. You get on a coffee table, you're pushing down at 150 pounds. Coffee table can only hold up 100 pounds. Well, guess what? You're winning that fight with 50 pounds. Coffee table pushes up with 100, you push down with 150, you win, and therefore you fall through the table at 50 pounds. So again, action-reaction. The reason we're all standing, we're all able to walk, the reason you can sit on your chair without falling through your chair is because your chair pushing up with the equal amount of strength that you're pushing down with. Alright, so when he's on the cliff, he pushes down with his weight, the cliff pushes back up on his weight, and therefore he doesn't fall. When he's in the air, he pushes down with his weight. Air tries to push up with the same force, which it does, but technically it cannot, because air can also move, right? A cliff is a solid object, therefore it cannot move. Air particles will just move to the side, so if you're more dense than air, you'll end up falling through air, just like if you drop a penny in water, the penny is going to fall to the bottom because it's more dense than water. So the same exact reason. So when you're on air, being more dense, you'll just fall through. Sorry, baby is screaming. Question number 3. Alright, so now we're going to use all of Newton's 3 laws and explain why it makes no sense that the coyote is able to stop in mid-air. So we're going to go through and use each of them. There are actually a lot of things that you can point out. I'm just going to stick with a few of them. Alright, so the first one. Objects in motion remain in motion unless acted on by an unbalanced force. So if you're ever running and you try and stop, the force that is stopping you is your legs pushing against the ground, and ultimately that force is called friction. So you run really fast and then you put your foot down and you kind of slide. That sliding you're doing is causing friction, and that friction is stopping you. So if you are in motion and you put your foot down on air, air is not going to give you any friction, therefore you're not going to be able to stop. So that just makes no sense. So therefore, based on the law of inertia, you should just keep running off the cliff and you should just fall. Gravity will pull you down. You won't fall straight down, you'll keep going on kind of a pattern like this, like my mouse is moving like this. Whereas in the Wile E. Coyote, he just runs off the cliff and then falls straight down, which makes no sense at all. So again, objects in motion remain in motion. Therefore, if you have nothing under your feet to stop you, you have no way to apply a force equal and opposite in direction in order to stop you. Alright, F equals ma. If you're stopping, you have to change speed. So he was moving some speed and then he went to stopping speed. So therefore, there must be a force present. But again, there's no ground to push off of, so if there's no ground, there's no friction, and if there's no force, then you actually can't slow down. So you can't slow down on air. You can run all you want, or you can try and move your feet all you want, but you actually can't stop. 3 is action-reaction. If you're pushing with X amount of force, in order to stop, something's got to push back. You can't push on air. Again, it all comes down to the same idea. When you're on air, you can't push down because the particles that make up air are just going to move away from you. Gases are free to roam. So therefore, when you push down on a gas, it just moves over to the next spot. It's not there. It's not a solid. It's not like a liquid. Therefore, when you push down on it, it just moves away from you. So without having anything to actually physically push you back up, action-reaction would tell you that you should just keep falling instead of coming to a complete stop. It makes no sense to be able to stop in midair. Question number 4, what do you think the difference is between mass and weight? We're going to be talking about this in today's lesson. That is the whole point of the challenge, so we are going to go over that. So today we're going to be talking about mass and weight and the various characteristics. So again, follow along with us. This is something that a lot of people really confuse. People use the words mass and weight interchangeably when they are not interchangeable, and they mean two completely different things. They are related, but they mean two completely different things. So pay attention. On your test, you're definitely going to have questions like, hey, describe the difference between mass and weight, or I'll try and catch you in scenarios where I want mass or I want weight, and I'm going to try and catch you saying something that's incorrect. Alright, so our goal for today is that you guys would be able to figure out how your mass and weight would change if you go to different planets, or honestly, if you just get further or closer away from the center of the Earth. The objective for today is that you'll be able to apply your knowledge of mass and weight to Newton's second law, which is F equals ma, in order to solve unknown variables, which is very similar to what you've been doing the last 2 days, except now we're going to have a specific A, and we have a specific F, which we're going to talk about a little bit later. Okay, so to start this out, if you look at your hands, stand on the floor, drink a glass of water, breathe some air, everything that we do or see or can touch or feel, we're all surrounded by something that we call matter. The whole universe is made out of matter. So let's talk about what matter is first. Alright, matter is anything that has mass and takes up space. So we're going to talk about mass a little bit later, but let's break that down a little bit further. So what does it mean to take up space? So if we use you as an example, you're made up of matter, and you and another student can't be in exactly the same spot at exactly the same time, right? You can't be sitting at your desk and have your friend sitting at your desk too. There's only one way a person can be at a single space at a single time. So that is because you both take up space. Therefore, if you take up space, you can only occupy space at one spot. That is part of the definition of matter. Right. Another example is a bath. When you put your foot in a bathtub, the water is going to rise up. Or if you get in a bathtub, the water level rises up. And again, that's that same idea of taking up space. As you put your foot in the bathtub, the amount of space that your foot takes up is the amount of water that gets displaced. Water is going to rise up by that amount. So that's another example of what it means to take up space. Right? Matter is made up of these things called atoms. Atoms are the smallest particles of matter, and there are smaller things. We have been able to break the atom down further and further, but for now, let's just go with this definition. Atoms are the smallest building particle of matter. Alright, atom has a positively charged nucleus. That's an important one to remember. The nucleus is made up of these things called protons and neutrons, which we're going to talk about in a little bit. Protons and neutrons are about the same size. They weigh about the same exact amount. The difference is protons are positive and neutrons are neutral. They have no charge. So if you take something that has no charge and you mix it with something that has positive charge, the net cluster, that grouping, will end up being a positive charge. So that nucleus ends up being positively charged. All right? Surrounding the nucleus is these things called electrons. Electrons are negative, and they actually go around. They like to picture it like in orbitals, like they go around in almost a circle or ecliptic fashion. But really, they're bouncing around all over the place, phasing in and out of energy levels, all sorts of really crazy things that you'll learn about in chemistry. For right now, we'll just picture them as surrounding the nucleus, as in they're going around. And just to give you guys a frame of reference, if the nucleus was about the size of a golf ball, the closest electron would be about a mile away from the nucleus. That would be pretty standard. Right? And just to put it on a scaling perspective for you to understand. Alright, so protons are positive, neutrons are neutral, and electrons are negative. Okay, so it's very important to remember. A lot of people make the mistake protons are positive and they say neutrons are negative because they both start with N. That is incorrect. Neutrons, neutral. Neutrons, neutral. And electrons are negative and they chill on the outside while protons and neutrons are in the center. Alright, so now let's think about the following, because today the whole goal is to talk about mass and weight and to kind of differentiate between the two. But if you take a bowling ball and a basketball and you hold them up, they have the same volume, aka they're the same size. They could even be the same color if you wanted. But there is a really big difference, right? If you drop both of those objects on your foot, you're going to feel a big difference. And if you don't believe me, feel free to drop a bowling ball on your foot and let me know how that goes. One of the differences between those two is weight, right? A bowling ball weighs a lot more than a balloon does or a volleyball does, even though they could be the same exact size. Weight is the measure of the gravitational force an object has due to the planet's gravitational acceleration. So that's something that you guys should underline on your worksheets. It's very important. Put a star next to it. It's a huge topic. Weight is a measure of gravitational force. Weight is a force. Alright, so if you jump in the air and you land on somebody's face, your weight is going to be the force that that face feels. And again, if you don't believe me, lie down on the ground, I'll climb up on a desk and I'll jump off the desk onto your face. And you can let me know how that feels. It's a force. The weight is a force. When you go to pick somebody up and you go, oh man, he's too fat, I can't lift him. That's because weight is a force. It requires X amount of newtons or X amount of force for you to be able to lift them. Again, you guys are used to using pounds, which is fine, but that's the same exact idea. If somebody weighs 150 pounds, it requires 150 pounds in order for you to lift them. That's how much force it would take for you to lift them. So weight is a force. That force is specifically dependent upon the gravity of whatever planet you're on and where you're situated on that planet. So if you're closer to Earth's center, you actually weigh more than you do if you're actually further away. So if you're in an airplane, you actually weigh a few pounds less. It's only like maybe 1 or 2 pounds less. And then obviously the further out you get to space, the less and less you weigh because the further and further you are away from Earth. My babies are crying something fierce. I'm not sure if you can hear them. So weight is the measure of the gravitational force an object has due to a planet's gravitational acceleration. And we haven't learned about gravity yet. That's actually a pretty advanced topic. And we'll get to that by the end of the year, but force is always F equals ma, which we learned about already. In particular, the type of force we're talking about is called weight. So sometimes you'll see it written as Fw or Fg, or just W in general. I tend to write Fg. I know I don't have that on the screen, but I tend to write F with a subscript G instead of a subscript W. Equals M. M is just mass, it stays the same, and then A, and then notice the subscript G, and that G is to specify gravity. So as opposed to acceleration from a car, acceleration from a bullet, this is acceleration of gravity, so they write AG. Now if it was acceleration of a car, you could write A little c. You can write A little b for bullet, whatever it is. It doesn't matter what letters you pick. The letters are there to help you organize. Alright, so weight depends upon gravitational acceleration. Since gravitational acceleration changes from place to place, your weight changes from place to place. That's a very important idea. If you go on the moon, your weight changes. If you go in an airplane, your weight changes. If you get closer to the center of the earth, your weight changes. Your weight is constantly changing. Mass, on the other hand, is how much matter is in an object. Alright, so mass is literally how much stuff is in something. It's how much matter you have. How many atoms actually physically make you up. So when you lose weight, it's a little bit trickier because usually when people say they want to lose weight, what they really want is to lose mass. You want to lose how much stuff you have. So right now, like I have love handles. If I say I want to lose weight, technically you could just tell me, hey, stand on top of a desk. Because the further away I get from the center of the earth, the less I weigh. If I go in an airplane, I weigh less, right? But I didn't actually lose weight by going in an airplane, even though I technically did. So the correct thing that people should be saying is I want to lose mass, not lose weight. Because you can lose weight just by jumping. You jump up once, and I'm not talking about burned calories, I'm talking about weight is a product of gravitational acceleration, and if you jump in the air, you're further away from the center of the earth, and therefore you weigh less. So you can weigh less just by doing something like that. Alright, so your mass does not change from place to place. That is a huge one. If I go on the moon, I still have the same mass. If I go on the sun, I still have the same mass. If I go on an airplane, I still have the same mass. Weight changes, mass does not change. Alright, so again, remember, weight is the measure of how hard gravity is pulling down on something. The pull of gravity is 9.8 meters per second squared on Earth. We can use it as an approximation. Again, if you climb to the top of a mountain, it might go down to 9.79. If you go in an airplane, it might be like 9.68. It really doesn't change that much from 9.8 meters per second squared, so that's kind of what we see. A lot of times in elementary school, they'll even tell you to round that to 10. In this particular class, we're going to be using 9.8 meters per second squared as Earth's gravitational acceleration. Alright, so to sum up everything I mentioned so far, mass is a property of an object, whereas weight is a force, not a property of the object. Alright, so for example, I take a pencil. Properties of this pencil are, it's orange, it's about 2 inches long, it has a pink eraser, it has graphite in it, and it has X amount of atoms in it, right? If you picture this pencil, and I take a bunch of little atoms, and I put them together, bunch them, and eventually you get a pencil, right? It's like taking Play-Doh or something. You take a bunch of little balls of Play-Doh, you keep putting it together until you build a pencil. So that's called mass. How much mass the pencil has is a property. If I take that pencil and I bring it up in a spaceship, it is still a pencil. You don't just go up in space and the pencil magically turns into a Cheeto, right? It's a pencil is a pencil. You go into space, it's the same color, the same, everything about it is the same, right? It is all the properties of the object are going to stay the same. So like if I go to Mars, right? The pencil is still orange, it's still about 2 inches long, it still has a pink eraser, still has graphite in it, and it still has the same mass. It has X amount of atoms in it. What changes is the weight. If I go to Mars, the weight of the pencil will change despite the fact that the rest of the properties that have to do with the pencil are the same. Alright, so now let's try out some of these problems mathematically just to see how they work out. Again, you've been doing them for the last 2 days. The only difference now is I'm going to specify a type of F and a type of A. Alright, so we have my homie Isaac Newton weighs 5 newtons and is chilling on his crib on Earth. We want to find his mass. So first thing you want to do is picture your situation. Alright, so we have Isaac Newton there chilling in his castle. Alright, our second step is going to be to write down those given. So we have weight is 5 newtons. Alright, we know he's on Earth, so Earth is a given there because Earth tells you that the gravity, or gravitational acceleration, AG, is going to be 9.8 meters per second squared, and we are looking for mass. That is our question mark. Alright, step 3 is going to be to select our equation, so I'm going to pick W equals mg. Again, generally I write F equals mag. Is usually how I do it. It's still F equals ma. It's just the specific F we're talking about is called weight, and the specific A we're talking about is called gravity. So again, sometimes people write it as W and G. I don't care which way you use it. It doesn't matter to me as long as you know what those things stand for. Alright, so now we need to check all our units, make sure they match up, which they do. We have weight is in newtons. We have our acceleration is meters per second squared. Nothing fishy there. So we're good to start. Alright, so now we're going to plug and chug. We have W is equal to mg. Our weight is going to be 5, so we're going to have 5 on the left-hand side of the equal sign. We're going to have 9.8 m on the other side of the equal sign. If we want to isolate that m, we need to divide both sides by 9.8. So we end up getting 5 divided by 9.8 is going to give us our m. And that should give us about 0.51 kilograms. Alright, again, don't forget your units on that. Alright, question number 2. Psyduck is sitting on planet Platypus. The gravitational pull on planet Platypus is 8 meters per second squared. If Psyduck has a mass of 20 kilograms, what is his weight on planet Platypus? Alright, so I want you guys to try the next one out. I'm going to give you guys a few seconds before we go over it. There we have Psyduck chilling on the planet Platypus. Alright, we know the following givens. We know that the gravitational pull on planet Platypus, I wrote GP for gravitation and then P for platypus. Again, you could have wrote AP for acceleration on planet Platypus. It really doesn't matter. Is 8 meters per second squared. Our mass is 20 kilograms. And we are trying to find the weight on planet Platypus. Alright, so again, we set up that formula. W equals mg. Make sure our units are correct. So far, our units and everything's good to go. Now we just got to plug and chug. Alright, so we have W is equal to mg. Our W is what we're looking for. We know that our g is 8, and we know that our mass is 20. 8 times 20 gives us 160 newtons. So Psyduck weighs 160 newtons on that particular planet. Alright, so now I want you guys to try some out on your own. Remember that weight is a property of a planet and its gravitational force. Mass remains the same no matter what planet you're in. So when you set up the equation W equals mg, the W and the g you choose have to be related to each other. For instance, you can't pick the W from Earth, your weight on Earth, and use the gravitational pull on Mars. That makes no sense. Your weight on Earth is determined by the gravitational pull on Earth. Your weight on Mars is determined by the gravitational pull on Mars. So when these problems get a little bit trickier, make sure that your givens all line up with each other, otherwise you can't put them in an equation together. Here's a cute rhyme just to help you guys remember it. Mass stays the same wherever you go. Weight is always changing, just so you know. Oh, isn't that cute? I thought it was cute. Alright, example number 2. This is a really hard one. I want you guys to put a huge star next to it. Alright, I want you guys to try the next one out. I'm going to give you guys about 30 seconds to a minute to finish it, and then we'll go over it together as a class. Alright, so weight is a product of gravity, and if you guys ever watch Dragon Ball Z, you know that this is what Goku does. He goes in his spaceship and he sets the weight to like 100 times gravity of Earth. Therefore, when he tries to stand up, it takes a lot more strength to stand up or to jump, and that's where he trains. And then that way, when he comes back to Earth, he can punch really quickly or easily because he's been conditioned to work in such a strong gravitational pull. Alright, so example number 2, please put a star next to this one. It is really tricky. Psyduck is sitting on planet Platypus. The gravitational pull on planet Platypus is 8 meters per second squared, like we discussed earlier. If Psyduck has a weight of 200 newtons on planet Platypus, what is going to be his weight on Earth? Alright, so we have a lot of givens here that you need to pull out and be very careful for. Alright, so first we're going to draw our situation. We have Psyduck, he's chilling on planet Platypus, but then we want to figure out how much he weighs on planet Earth. So we have 2 different planets, which means we're going to have 2 different accelerations, and we are going to have 1 similar mass. Remember, your mass is the same no matter which planet you go to, so that's kind of the guy we need to fight our way to. So next thing we're going to do is we're going to pop out our givens. We know that our gravitational pull on planet Platypus is 8 meters per second squared. We know that we weigh 200 newtons on planet Platypus, and we want to find the weight on Earth. Earth being a key word there because Earth also implies that we know acceleration of gravity is going to be 9.8 meters per second squared. So Earth is also a key word there. Alright, so when you write down those givens, I have GP, so gravity on Platypus, is 8 meters per second squared. WP, weight on planet Platypus, is 200 newtons. And we are looking for WE, or my weight, on Earth. And again, you could be writing FE if that makes you happier instead of weight. Weight is a type of force. That's fine. That might confuse people later on when we do work, but that's cool for now. Alright, so now we're going to find an equation. Our equation is obviously F equals ma, or in this case we're using W equals mg just temporarily as a placeholder, just so people can understand the words, just so until people get used to what these things stand for, and then we'll go back to using F equals ma. Alright, so we have W equals mg. We're going to be plugging those things in. You have to remember that your g and your W have to be related. Okay? So here, the goal, what do we have, what do we need? This step's actually going to come in handy. What we want to have is WE, or our weight on Earth. What we need to have is mass. If we know what the mass is on Earth, we know that gravitational acceleration is 9.8, and we can multiply those 2 numbers. So if you want to find WE, we need to have m and g on Earth. Our problem is we don't have m. Therefore, if you look at your givens, we have gravitation of platypus and our weight of platypus. If we can solve for m using those 2 values, we can then plug that m in and solve for our weight on Earth. So follow along with me. It's a little bit tricky. All right. So here are all our givens. So first, what we need to do is we need to solve that first equation for m. Then we're going to plug m into the second equation and be able to solve for WE. It is a two-step problem, which could be a little bit tricky. So again, follow along with me. So plugging in, we have 200 is equal to 8m. All right, if I divide 8 on both sides, all right, that's going to give me 25 kilograms. Now that I know my mass is 25 kilograms, remember, no matter what planet you go to, mass stays the same. So on Earth, I must also have 25 kilograms. And because Earth's gravitational pull is 9.8, I simply got to take that 9.8, multiply it by 25, and now I'm going to find my weight on Earth would be 245 newtons. So if you weigh 200 newtons on planet Platypus, you will weigh 245 newtons on Earth. Alright, so now I want you guys to try out your problems. I incorrectly numbered them, but you get the idea. Question number 5, 6, 7, 8, 9, 10, and 11. I'm going to give you guys about, 10 minutes-ish. Alright, again, you guys are working on 5, 6, 7, 8, 9, 10, and 11, and I'll give you guys about 6 minutes to do that. Alright guys, if you can give me your attention, we'll start going through these answers. I'm going to skip the math problems, so I'm going to skip 5, 6, and 7. I'm going to jump right to question number 9. Which weighs more? An 88 Newton object on Earth or an 88 Newton object on the moon? Why or why not? All right, this is a really good question. It's a trick question because the question says which weighs more. In terms of weight, weight is a force. So if you get hit with 88 newtons on Earth or 88 newtons on the moon, guess what? You're still feeling 88 newtons. 5 pounds on Earth, 5 pounds on the moon, 5 pounds on the sun is still 5 pounds. It doesn't matter where you go. So the question is a little bit tricky. If I said which has more mass, an 88 Newton object on the Earth or an 88 Newton object on the moon, your answer would be an 88 Newton object on the moon, because on the moon you should weigh less. Therefore, if you weigh more, it must be because you have more mass. Therefore, objects with more mass are going to weigh more. A car weighs more than you do because it's more massive than you are. Question number 10. When you diet, people commonly say that you're losing weight. What are you really losing? All right, you guys should know the answer to this one based on what we talked about earlier. We specifically even talked about this. But you're actually losing mass. You don't lose weight. But with that said, by losing mass, you technically also lose weight. So it's not completely incorrect to say. But if someone's ever like, oh man, I'm trying to lose weight, you could technically just say stand on a chair. And they would lose weight just by doing that and getting further away from the center of the Earth. Question number 11. Can two different masses have the same weight? How? This is a very good question. It's a college level question. Two different masses can have the same weight if they have different accelerations. Remember, F equals ma. So let's say you have one mass is 1 kilogram and our force is 10 newtons. It weighs 10 newtons. Alright, so that means our acceleration must be 10 because 1 times 10 is 10. Alright, let's say we go to another planet and you have a mass of 10 kilograms and you still want to weigh 10 newtons. In that case, your acceleration would have to be 1. Therefore, you'd have 10 times 1 is 10. So can you have the same weight? Yes, you can have the same amount of force. The difference is you're going to have different accelerations for two different masses. Alright, so now we're going to jump down to that exit assessment. So follow along with me. Fill in the numbers that you are missing on your sheet. That way you're able to do them. We have questions 1 and 2, so please fill in the following numbers and then we'll go over it in about 2 minutes. Alright, so let's try this out. What is the gravitational acceleration of planet Luffy if you have a mass of 2 kilograms and a force of 4 newtons? Alright, so what we're going to be doing is taking that 2, dividing it on both sides, and you should get an acceleration of 2 meters per second squared. Question number 2. Teletubby weighs 100 newtons at a local doctor's office. How much mass must the Teletubby have? Again, tricky problem because they only give you one given in terms of the 100 newtons. And that's obviously a force because you can tell that it's in newtons. The other trick part is that you're on Earth. It says a local doctor. That means we are on planet Earth, which means our acceleration must be 9.8. Therefore, if you take 100 and you divide it by 9.8, you get a mass of 10.2 kilograms. Alright guys, that's it for me. Thank you so much for another good day, and we'll do this again tomorrow. Take care.